This is lesson 12A, transformations of functions. Now we're going to revisit a little bit of our geometry and look what happens to graphs if we change the value of the function by adding, subtracting outside of the function or inside the function, or adding negatives inside and outside the function. So you might have remembered these back in geometry. These are called transformations, right? And there's three types of rigid transformations, and that's translations, and we have reflections, and we also had rotations. We're not going to have any rotations here. We're only going to have translations and reflections. So just a little reminder that if we take any function and we just add or subtract a number to it, it just moves that function up and down. So the ordered pair that we end up with is just a reflection, no pun intended, of whatever that value of k is. So if it's a positive k, I'm going to take each of the y coordinates and add k to it. Same thing if it's a negative k. I'm just going to subtract k from each one. Okay, move it down. Now if we have it on the inside, this f of x minus h, you might recall that changes everything from left to right. So for this case, we're going to take the x coordinate and we are going to add a value of h, and y will stay the same. Same thing here. If we have x plus h, we are going to subtract that value of h. So you might recall it goes the opposite direction. So a minus h actually moves to the right. Okay, so notice that minus h moves to the right, plus h moves to the left. Now we also have reflections over the x-axis. So if we have a negative on the outside, that's just going to change all the y values. The y values become the opposite. So we have x comma the opposite of y. And then if we have a negative on the inside of the function, that's going to be a reflection across the y-axis. So we'll have all the x values will be the opposite. So that's just a review, and we're going to use this to move functions around a little bit just as a little reminder. So here's some functions. Right, so something like this, we just have to say, let's see here. It says sketch each transformation, the results in the graph of g of x. Okay, so we're just going to, given this, and we're just going to write down like what each part means. Okay, so if we're going to do that, that's going to move us down 5. So it's nothing more than just taking each point, right, and just moving it down 5. 1, 2, 3, 4, 5. All right, we can do this. 1, 2, 3, 4, 5. And then this one. 1, 2, 3, 4, 5. And this will be, I can see that these are going to stay on the same level, so I'm just going to do this, and then of course right there in the middle. Now one thing to remember is that these should be the same exact shape, so we're not changing anything about the size, right, because it's rigid, and that's rigid. Okay. Now see if you can try this one right here. Which direction does that move? The minus 3. And then let's skip the middle one, we'll come back to that, and then do also this last one. Okay, so they should have this where it moves to the right 3 times. And then over here we're going to have a reflection. Right, reflection over the y-axis. Right, so I just took each x value, if it was a positive 3, it made a negative 3. And vice versa. Like this negative 5x value became positive 5. So I just changed out the x values, made them opposite while the y values stayed the same. Alright, we'll come back to this one because on the next page, move forward, it actually talks about what happens when there is a fraction here. So let's go to here. And if we have a number multiplied in front, it's just a regular number like 2, 3, 4, 5, right? Right. What that does is it actually dilates, right, or stretches, right? So this is another transformation where the shape actually does change, right? So if this is the case. Since we're multiplying, remember this is just like the y coordinate. F of x is the same as y. We just started calling it f of x instead of y. But this really just says multiply whatever number this is, multiply the y coordinate by that. Okay? So the y coordinates become twice as big. And if we have a fraction here, it's going to be a shrinking factor, right? So, but it's still the same concept. Now, what happens if we have the value on the inside? What does that do? Okay, so it's actually the opposite, kind of like with the before. The plus moved to the left, the minus moved to the right. So when we have just a bx, that's actually going to be a 1 over b times our x coordinate. And the y stays the same. Same thing here. If we have 1 over b, we have a fraction here. That's just going to be a regular b. Whatever that number is on the bottom, we're just going to multiply that by x. Okay. And a little side note, why is that the case? Let's say, like if we have some number like b times x equals 4. How would I solve for x, right? I would divide both sides by b, right? So my x value would actually be the number divided by b. So that's why this is 1 over b when we just have a regular b here. Same thing here. If I had 1 over bx equals a number, I'd multiply both sides by b, right? So if I had this equal to some number, the way to solve for x would be to multiply both sides by b, right? And I just have b times my x value right over here. So that's why we have it in that situation. So we want to figure out, well, how can we use, let's go back and actually use this, because we had the last one. So let's go back. We have a negative here, right, on the outside, right? So that's kind of like this right here, or up here, right? We already did that, yep. The negative on the outside. But then we have a 1/2, right? So that's just going to make all the y coordinates, right, just a half smaller, right? Just a half smaller. So all we have to do is, on top of reflecting it, right, we also have to make all the numbers smaller. So you might have to do this in 2 steps. Okay? So if you want, you can do the reflecting first, or you can take the half first. Okay, we got 2 steps to do. I'll put this part, the orange. So we got the 1/2. Let's take just half of everything. Okay, so if I take half of every y value, this 4 will become down here the 2. Right? Half of 0, right? That won't change. And I gotta find, like right here, half of, that's 3. That goes to like 1.5. Or we could pick a better number. Let's say half of 6 is going to be 3. Right there. Right there. So we have something that looks like this. There we go. Something that looks like that. And then we can do the reflection now, right? So now I'm going to reflect it. All the positive y's will just become negative y's. So I have this. I have here. This one right here at 3 will go down to -3. And that will go right there. So our final will look like this. There we go. A little straighter. Okay. Now we could have done this in the other order. We could have reflected it first and then just taken the half. That would have been fine as well. Alright. So let's go back to where we started and look at these examples that give us a particular range. They don't give us the actual function, but they give us, well, what the function is doing to the original. Like they give us a new function, h of x, and says, take whatever function this is, and we're going to do, let's say, these 2 or 3 things to it. And the domain and range numbers are going to change, right? Because we're adding, subtracting 2 x's and y's. So we have to look at 2 things. We have to know which of these transformations are going to change the domain, which ones change the y's. So here we can get, what we do is we say anything, let's see, domain of the function is this, right? The domain is going to be affected by anything on the inside of the function, parentheses. So this right here is going to be changing the domain, the x plus 1 on the inside of the parentheses. Anything on the outside the parentheses, this 2 and this minus 3, that's going to alter the range. And that's going to change the range. So we have to know that because we need to do these carefully. So you recall that this x plus 1 actually moves the graph to the left, right? So we're going to do the opposite. We're going to subtract 1. We're going to move everything to the left one. So we have this range already that is right here. And we're simply just going to subtract 1 from both parts. Right? So my new domain will just be from -7 to +7. Okay, nothing more than that. Now my range, okay, I'm going to start with this. It's going to do two things. We're going to have to multiply it by 2, then do the adding subtracting. So this is order of operations. You might say, well, should I subtract 3 first and then double it? Or should I double it and subtract 3? Because you'll get different answers. So order of operations says, if you're plugging a number in here, you would multiply whatever this value of f of x plus 1 is. First thing you would do would be to multiply it by 2. So we're going to make sure we do that. We're going to say times 2 times 2. All right? So this is the 2f of x part right here. So we'll get -6 to 14. And then we're going to subtract 3 from both of those. That would be the second step you would do in order operations, the add subtract. Okay? So we have -9 and -11. So those would be our new domains and ranges, right? Our new range would be from -9 to 11, started here, ended up here. Right? So without actually knowing what the graph is, we can figure out, approximately how big or small or where it moved to. Okay, let's try another. This one gives us a table. Do a little bit more, but same thing will follow. All right, so let's just evaluate this. Let's just plug this in and see what number we get. We just got to be careful as we're writing our work down that we don't rush it and make any arithmetic mistakes. Probably the most common mistakes on these problems. It's just going too fast, and then we have a wrong answer. Okay, so take your time. It's a little bit bigger. There we go. All right. So we have h of 2. So we're going to do. So I'm going to have 3 times k, and I have 1/2 and my times 2 plus 2. All right, so I just took this whole function, and this is the value of x. X equals 2, so I'm plugging 2 in for that value. All right, simplify as much as possible. So we have 3k, parentheses here. Half of 2, of course, is 1. And then we go up and find, well, what does this actually equal? What does k of 1, what's that value? All right, so we go to k. Right here, our function k, find 1. All right, that's right here. So I'm going to substitute k of 1 is going to equal 3. So I have 3 times 3 plus 2, which is 11. So h of 2 equals 11. So if I was going to graph this, 2, 11 would be the coordinate where this particular point would live. All right, so try the rest of these, see how that works for you, and then check your answers in a moment. So go and pause and try the rest of these. Okay, so hopefully you got these answers. Do show the steps here and how these are being calculated. Try not to rush and just write the number down and say, I did in my head. This is when they say justify your answer. It's part of the answer, especially on AP tests. You have to have this written down, right? Otherwise, we're going to get a bunch of right answers and not a very good score on our tests. All right, so let's do the same thing. So we did it with just domain and range, and then we did it with a chart. Right? Let's do all the representations. Right? Now let's do what happens to the graph. Right? That's a good jump. And you might have seen this before, right? So maybe it won't be too new, but good to review. So just ask yourself, what are each of these things doing, right? What are the different parts of this doing based upon what we've done so far? So of course, x plus 3, that's going to move the graph which direction? Left. And then the minus 4, right? That's going to move the graph down. And then we're going to have to multiply it by 2. Multiply the y values all by 2. So we can do that, of course, from here. So we can draw our base function, right? X squared looks like this. We know what that looks like. Goes through 1 1s and 2 4s, right? It's something like this. So we can just imagine translating this. Right? And it's good to do the translations first and then do the stretch afterwards. So I'm going to move everything 3 left and 4 down. Right? 3 left and 4 down. Now it has exact same shape, so I don't really need to translate point after point because I know what x squared looks like. Well, let's do this in a different color. Let's say now we're at negative 3, 4 right down here, and I know it's going to go up 1 over 1, and then here. Okay, so now we have that. And lastly, let's do our final graph where you double all the y values. Okay, starting from here. Well, not starting from here. We're going to keep this the same, the vertex. But everything else is going to go up a little bit more, right? So that's only 1 away from our vertex. It's now going to be 2 away. So you can see this makes it a little bit more narrow. Same thing here. We would be right up here. Now it's going to be much higher. And the distance is going to double. So instead of going like up this much, we're going to go all the way up to the top. So we're going to go all the way up here. Right? So we're going to go all the way up to right here. Okay. Well, make sure we understand why we picked those places right there. So this is now twice as big. So like if I was still back in the origin, instead of going up 1 over 1, I'd have to double that, right? It'd be up 2 over 1. And then the next place, right, which is normally going to be, right, 2, 4, right, I'd have to double that. 2 would now become 8. So that's why this is so much higher. I'm going from now negative 4 all the way up to positive 4. Right? Okay. So let's see if we can do one more. It's got a few more steps in it. Okay. All right. So we're once again going to have our translations, right? Just moving it left, right, up, and down. So the minus 3, what does that do to the graph? All right, that's going to move it right. And then the plus 1 is going to move it up. And then we'll have 2 more steps after that. We're going to have to do a reflection, right? And we're also going to have to do this right here. Now you might go back and say, what does the 1/2 do? You go all the way back here and use your notes, right? That's going to be a dilation, right? We're going to take a half of all the y values. So it might be a good idea to create a t-chart on this and actually look at it and make sense out of it rather than trying to do it strictly graphically, right? There's a lot going on, 4 different steps. So if you want to, we can also use Desmos. Let me get that together real fast. That'd be a good problem to do. Let's see here. Okay. So I got my base function here. My base function, which is x to the 3rd, right? And I want to do all these transformations. So let's do this piece by piece. And we can see what it does to the graph. Here. That way. A new function, I'm going to call it g of x. Oh, doesn't like that. Let's just do y. Yeah. Y equals, and we're going to do one thing at a time, right? We're going to do f of x minus 3. Right, so we can already see the graph move to the right 3. And then we're going to move it up 1. Okay. And then we can see we're going to now do, let's do the 1/2 in the front. So I can go over here and say, let's make all those y values half as much. So there you go. And you see what happens to the graph here, right? This is right there. So has a little bit of a compression, right? And then we're going to, at the very end, add a negative onto there, right? That's going to be a reflection, right? Notice how it's not over the y-axis, but over the center, right? So a lot going on here, 4 different things, and the nice thing here is that we could actually click on this table, and it'll give us what the coordinates are. And those aren't really good coordinates to start off with. I'd probably start off with 1, and go 2, 3, 4, and 5. And maybe more, 6. That'd be off the graph. Yeah, let's stop there. Yeah, so those would be the coordinates, right? And we can do these step by step if you want, right? And it'll give you each one of those. Right, so however you want to do that, but it's a good exercise to try to do this without Desmos, but at the beginning, you know, it's a good tool to use until it makes sense, okay? Just think about using this as like training wheels. Now, if you like, you could also do the reflection and the 1/2 compression first, and then just move that entire graph over, right? So we can do these in different steps. If we're not like finding domain and range, it really won't change what our graph is doing, right? So if that's easier, that's better, you can try that. Right, but always start with your base function first, and then go from there. Right? I'm just going to put this, ends up at, looks like 3. Got my graph here. Yeah, 3, 1. It goes down. Oh, that's that right? Oh, yeah, yep, 4.5. Okay, yep. Good. Good. And at 5 right here. And then that would be down here at 5 and -3. All right. Oh, that's not right. One more time. 5. Yeah, it didn't look symmetrical, so I knew something was wrong. There we go. Alright. Perfect. Okay. Love our graphing calculators, and we love Desmos to help us out. Alright, let's get moving down to another one that has to do with the domain and range. But now there's a lot more going on. So before, look at the first example of this type. And we just did basic translations, and we stretched a little bit. Now we're going to do an awful more with it, right? We have every single thing going on here. We have stuff on the inside, stuff on the outside, so we have to be very careful how we go about this. So recall that everything inside of here, that's what's going to affect the domain, right? That's going to affect this right here. Notice how this is an interval notation instead of set notation. That's not going to change difficulty. It's just written a little different. And then we have this -2 and +7. That's going to affect the range. So there's a couple ways of doing this, but I'm just going to take each one of these and say I got my 1/3 times x + 3, and I have my -5. And I'm just going to solve this right, by multiplying both sides by 3. So I have x plus 3 now equals negative 15. And then I'm going to subtract 3 on both sides. So my new lower bound would be x equals negative 18. Then I can repeat this, of course, for the upper bound. All right, so repeat the same process. 1/3 x plus 3 equals positive 5, and then same steps. So I'll have x plus 3 equals 15, and then x will equal 12. So my new domain will be from negative 18 to 12. So for the range, just remember that this part right here of our function is just a y value, right? So we're plugging this in and we're getting the lowest possible y value we can get is negative 15, or the highest is positive 15. So I'm just going to take this equation, right, and just use that and plug in both negative 15 and positive 15. So I'll have negative 2 times negative 15. Right, plus 7, so that's 30 plus 7, that's 37. And then do the same thing with the positive 15. Plug that in for y. So negative 2 times positive 15. And add 7. So we have negative 30 plus 7, so that's negative 23. Now, be careful. This is now the upper bound, right? We plugged in negative 15, but we got the positive number. We plugged in positive 15, we got the negative number. So you do have to always write these from least to greatest, right? So it's 23, 37 for the range. All right, so that will finish up this page. So take a minute to go back and just see if you can rehearse these in your head, right? Make sure they make sense. And before you move on, right, we want to have a firm grasp of everything we've done so far.
All right, let's look at our last example. This time they give us the graph and the table, which is nice. Although if we didn't have this table here, we could still probably figure out the different numbers. But you know, it's nice to be more precise, right? So if you use the front page of the notes, it'll give you a little hint. But if you think you already got it, try to do it without looking, right? So ask yourself, what type of transformation will happen if you have the opposite of h of x, meaning what does that do to the graph? Now think about that logically, right? And think about that h of x, right? That's the same as the y coordinate. So really, it's just taking the negative, or even better, the opposite of all the y's, right? So if we keep the x's the same, right, but then all the y's are the opposite sign, what does that do to the graph? Right, so if you think about it, hopefully you come up with, well, that's a reflection, right? That's a reflection across the x-axis, because the positive y's become negative y's, and anything that's graphed down here will become a positive. It's going to be up here. So that's a reflection. Right, so we want to start internalizing what this actually means geometrically, and not rely on some chart and looking back at it and seeing what you should be doing, because you can't use that on an actual test, right? We can't use that front page. Okay. So all the y coordinates are just going to be the opposite sign, right? So I can go to negative 2.5 and positive 6. So negative 2.5 and then positive 6 right there. And then just go right here. 2, of course, there's no opposite of 0, so all the zeros will stay the same at negative 2, and at 1, and at 4. Those don't change. And then I'll have negative 1. We'll change that to a negative 5. So at negative 1, I'll have negative 5 down here. And then at positive 2, we'll have positive 4. And at positive 3, we'll have positive 5. And then at 4.5, we'll have negative 6. 4.5, I'll have negative 6 down here. All right. So then we can just connect this carefully all together. Let's do just black. All right, so we'll start up here. Down, come back up, and go back down. All right. there is a reflection of the x-axis of the original graph. Okay. Now you can see what will happen here when we have the negative on the inside. Anything that's on the inside of the parentheses always affects the x-coordinates, right? So this time, for this problem, we're going to have all the x's switch signs while the y-coordinates stay the same. So that's a reflection over the what? Right? Over the y-axis. So we're going to take each of these and just change the x-coordinate, keep the y the same. All right, so we'll have negative 2.5 comma negative 6 will be positive 2.5 comma 6. And negative 2, 0 will be 2, 0. We'll have negative 1, 5 will be positive 1, 5. And 0, 4 will stay 0, 4. Okay, we have, see here, 1, 0 will become negative 1, 0. 2, negative 4 will be negative 2, negative 4. And we'll have negative 3, negative 5. And we'll have negative 4, 0. And lastly, we'll have negative 4.5, comma 6. All right, so we connect all those together. Something like this. Okay, and wait a minute, that doesn't look right. Let me double check this one. 2.5, was that 6? Negative 2.5, positive 2.5, negative 6. Okay, let's make one correction here. Negative 6 down there. Yeah, I know my shape is going to be the same, so as soon as that went a little bit different, something was up. Okay. Okay, there we go. Perfect. Okay. Now if you want, try the last two on your own, right? See what happens. Ask yourself, what will this do to the graph, right? What will having this 2x actually do to the graph? What will the 1/2 do to the graph? Think about that for a moment and give it a shot. So both of these are going to involve changing or altering the x-coordinate, right, because they're inside the parentheses. Just remember that when we have a 2x here, that really takes half of the x-coordinate. And the y stays the same. And then same thing over here. If we have half of the x-coordinate, that's really doubling the x. Okay, very important to remember that, right? When we deal with the x-coordinate, things are always kind of the opposite of what you think. So this is known as a compression, right? This is called a horizontal reflection, compression. While this is a horizontal, and when it gets bigger, it's called a dilation. Dilation. Notice how it's not dilation, but just dilation. Dilation. Okay. So we can use our table up here if we need to. It's probably a good idea. Let's go smaller. Let's see it. All right. So we are going to take half the x-coordinate and keep the y-coordinate. Right. So we have to be careful about this. We're going to take half of, let's say, this negative 2.5, right, which would be negative 1.25. And negative 6. Negative 1.25, and we're estimating, of course, and negative 6. Right here. And then we'll do half of negative 2 will be negative 1, and that's at 0. Half of negative 1 will be 0.5, or negative 0.5, and that'll be at 5. Half of 0 and 4, that stays the same. Half of 1 is a half, so half comma 0. Half of 2 and negative 4, so that's 1 negative 4. And 3, half of that is 1.5, negative 5. And 4, half of 4 is 2. And half of 4.5, that's going to be 2.25, comma 6. All right, so let's, oops, 6. Let's make that a little bigger, and we can connect all that together. So, as you can see, yeah, it is a compression. Everything just got really close to to itself. There we go, and then it goes back up, like so. Alright. So that is a compression by a factor of 2. So things got twice as close to one another, if you want to think about this 2 as being how close the points get together, right? So they're twice as close to one another, so they squish together or compress together. And that's why over here, like, well, these are about half as close, right? So this is going to spread apart. It's going to have the opposite effect. Okay? Now try that on your own if you can, since you saw me do this one. Try this one on your own. Okay, should look something like that, and it definitely dilated or spread apart, right? So all the points are half as close as they were before we started, right? Half as close. All right, so that is it for this one. Remember, go back and make sure you can reproduce any of these answers on your own and that they make sense. And we don't just want to copy things down and say we're done with notes, but really make sure if the numbers change here, you'd still know the steps and how to do it. That way you're prepared when you come into class. All right, take care.